Okay, so we're going to try to finish this lesson with the same problem, different method. And this is called either matrix algebra or inverse matrix method. Okay? So let me explain to you why it has these names. All right? So here's the basic idea. Okay? Let's say that you were given this problem. Let's see. 2/5 x equals 10. Let's pretend you were given this problem. All right? In algebra, you learned that you're allowed to do something to both sides. There are very little restrictions. Actually, you can divide both sides by 2. You can take the reciprocal of both sides. You can even square both sides, although you might produce false answers or something. You can put an ln on both sides. You learned that in Algebra 2 or pre-cal. You don't want to do like sine on both sides because those aren't one-to-one. But there's all sorts of things you could do to both sides. But there's only one thing that's helpful here. If your instructions are solve for x, you should probably multiply both sides by something, right? And what is that magic something that will make this all work out so great? 5 halves. Right. So 5 halves, because, listen, because it is the multiplicative inverse of 2/5, this serves as a useful something to do. Okay? So one of the hard things to teach about Algebra 1, I really find Algebra 1 hard to teach, is because the students are coming in with zero background of x, some of them. They don't know what x even means. So you have to explain why we're using x. You have to explain that x is actually a number and not just a letter. And that's confusing for some of the more immature ones. But I think the hardest thing to teach them is what you do to one side, you do to the other, and it has to be helpful. So, you know right now that you would multiply by 5 halves. You know that because it's legal and it's helpful. Teaching kids to do things that are legal is hard enough. Now you have to teach them how to do things that are actually going to make them progress in the problem. That's very hard to teach. So anyway, a lot of people struggle through Algebra 1. But anyway, we multiply by 5 halves, right? It's the obvious something that makes this work, right? From this point on, you don't even feel obligated to show work on the left side. In fact, you already know it's x. You already know this is whatever, 25. Okay? So let's apply that same idea to this problem. First of all, I'd like it to look like this kind of problem. So I'm going to write it a little differently. I'm going to write it like this. 2, -6, 4, 1. Variables and values we're equaling. Now this looks like my basic idea equation on the left, right? Looks kind of like this, doesn't it? What just happened? Looks like that kind of. In fact, now it's called a matrix equation. It actually has a name. This is a matrix equation. Okay. I already told you what these numbers are called in the last lesson, but we'll write it again. This is the coefficient matrix. This is our variables matrix. And this, for lack of a better name, I call the right-hand side matrix or right side matrix, because no one's ever seen me give me a better name for it. Okay? So what is the magic something that divides away the coefficient matrix? See, here the magic something that gets rid of the 2/5 is 5 halves. That's obvious, right? Although it might not be obvious to a 5th grader. You have to explain to them, well, 5 halves times 2/5 is 1. Right? Well, we need something that when we multiply it against this 2, -6, 4, 1, produces 1. What do we mean 1? We mean the identity matrix. So here's our goal now. Our goal now is to create a matrix which will sort of erase the 2, -6, 4, 1 and create the identity matrix instead. So what I really want is for this to be this. 1, 0, 0, 1. This is what I want. If I can find that magic something that undoes 2 negative 6, 4, 1, I'll apply it to both sides actually, and I'll end up with 1, 0, 0, 1 here. And my answer for x and y chilling on the right, because 1, 0, 0, 1 times xy is just plain xy. It really is like the uno, the 1 in the world of matrices. So now all that remains is I need to teach you how to find that magic reciprocal type matrix, the inverse matrix. Okay, so now that we kind of know what our needs are, I can erase this, and let's go over here and ask the question, how do we find a reciprocal matrix? Well, first of all, it's not called a reciprocal matrix, it's called an inverse matrix, okay? It's called an inverse matrix. But reciprocal is not a terrible name for it. It's just nobody ever says that. It's exactly what it is. It's going to be the multiplicative inverse. We're trying to make this a 1. So what you do, it's really very simple. To invert a matrix A, let's say it's got the numbers A, B, C, and D in it. The inverse version looks like so. Give myself a little more room here. I'll go on to the next line. A inverse, don't write 1 over A. We write A inverse is 1 over the determinant, that's just a number, times D negative B negative C A. Okay, so how did I get that? What I did was I swapped the A and the D around. So I actually put D where A was and A where D was. As for the B and the C, I left them where they were. These are the same spot, but I negated. So I changed their signs. So we changed the signs on the minor diagonal. But on this major diagonal, the top left down to the bottom right, we actually swap it. Okay, now this only works on a 2 by 2 matrix. The 3 by 3 isn't quite so simple. Okay? But this is the reciprocal matrix. All right? So for our problem, let me give myself a little space. We'll go back and actually do this now. The magic reciprocal matrix, you could say, or the magic inverse matrix, would be, first of all, 1 over the determinant. Okay, so that's always there. And then, in brackets, I will be swapping the 2 and the 1. So we're going to swap these guys around. And negating the negative 6 and the 4. So basically it looks like this now. 1 goes here, 2 goes here. This is a positive 6 now. This is a negative 4. And that's our inverse. You do have to find the determinant there. So remember, you just kind of cross multiply and subtract. So what is 2 times 1? Take away 4 times negative 6. Isn't that 2 minus negative 24? Turns out it's 26. Okay, so our magic reciprocal matrix is 1/26 of the matrix 1, 6, negative 4, 2. If you want to, you can distribute that in, or you can leave the 1/26 out front. It doesn't matter. Technically, you're supposed to distribute it in, but let's go on with the problem now. So if this was the magic something that sort of ruins and destroys and undoes the left side, we should be able to apply it to both sides of the problem and solve. So what I'm going to do is I'm going to squeeze in A inverse right there and right there. Okay, quick comment. Don't miss my comment, okay, because it's hard for me to write this, but it's easy for me to say it. Okay, listen. You're going to multiply this onto both sides. Okay? When you multiply a matrix against a matrix, don't miss this. You got to listen. There's nothing to write. Okay? Just look up here. When you multiply this matrix and this matrix together, it's very important how you write them. Okay? In matrix world, A times B and B times A are not the same thing. Matrices don't commute. Now, if you're doing a problem, 2 fits, times 10, 10 times 2/5, same thing. But not with matrices. With matrices, the order is very important. So you'll see here that I wrote the A inverse on the left side of the left side. And I wrote it on the left side of the right side of the equation. There's two sides to an equation. If I want to put it on the far left here, I have to put it on the far left here. You may not put the A inverse, for example, right here. You cannot do that. Because there's two reasons. One, that's not what you did on the left. You put it on the left side. You can't put it on the right side over here then. See? The other reason is, technically, you can't multiply a 2 by 2. Listen, you cannot multiply a 2 by 2 and a 2 by 1 in this order. So you cannot multiply this blue and this red because the sizes don't quite match. Okay? So just don't stress out about it, but make sure that if you're going to write your matrix on the left side of the left side, then you also write it on the left side of the right side. It's actually called left multiplication, is what it's called. Okay, so the other thing is, it's a real waste of my time and energy for me to pursue this side ever again. Okay? Remember, the inverse matrix was designed to cancel out the matrix. 2, -6, 4, 1, excuse me. So it's kind of like if you have 2/5 x equals 10, right? And you know you're going to be multiplying by 5/2 on both sides. I mean, who really shows their work on the left side from this point on, right? Nobody shows their work here. How many of you write 10 over 10 x equals 50 over 2? Does anyone ever write this step on the left? What's the point? I mean, this is going to be 1. Ooh, that's 1. Of course it's 1. You put the 5/2 there. Why'd you put it there? To make it a 1. So why are you trying to prove to me it's 1? What a waste of time that was, right? What happens is this problem becomes all about the right side. You know? The same thing is true here. This is a lot of work. If we're going to multiply A inverse, which is this garbage, times that, we're just going to get identity. Like, there's no point in even doing that. And also, nobody ever writes 1x, right? Does anyone ever write 1x? Anyone? Raise your hand. Probably not, right? The same thing is true. Nobody would ever write this identity xy. Because you know what identity xy is? It's xy. There's literally no point in writing. Okay? So I'm done with the left side. I'm totally done with the left side. I'm going to focus right here on the right side. I just need to multiply A inverse times -34, -3. Okay, so I know that's kind of hard to write down, but you don't really need to as long as you kind of know what you were intending to do. So we have xy on the left. Let me color code. Let me color code everything here. So I'm going to go with black. Xy equals and then I'm going to squeeze in my little inverse guy here. Let me color code. If I can figure out the answer to this problem, I'm done. I'm totally done. Okay, it's your choice. You can distribute the 1/26th into either matrix and then perform a matrix multiplication, or you can multiply the matrices first and save the 1/26th for later. I recommend you save the 1/26th for later. Who likes fractions? Let's just leave it out of the problem. We'll save it for later. Okay, so how do you multiply a 2 by 2 matrix and a 2 by 1 matrix? Do you guys remember how to do a dot product? We studied this just recently, dot products. Remember how you multiply 1, 4, don't miss this please. I need everybody's eyes up here. How do you multiply 1, 4, and 5, -7? You remember how to do a dot product, right? How do you do the dot product? Multiply your what? Multiply the x components, right? Multiply the y components. What do you do with the results? You add them. Okay? So you basically do 1 times 5, 4 times -7. Then you add the results. That's how you do matrix multiplication too. Okay? So look now at this problem. We're going to be doing a dot product for this row vector and this column vector. Okay? Alright, so we'll save the 126 for later, but let's do a dot here. What's 1 times negative 34? That's easy. Negative 34, right? What's 6 times negative 3? Negative 18. What do we do with these two things? We add them, right? So we basically do 1 times negative 34 plus 6 times negative 3. Okay? So this top number is literally just negative 52. Okay? Now let's go and let's dot product with the second row vector and the first column vector. Okay? So that's not too hard. It's just negative 4 times negative 34. Plus 2 times negative 3. This is minus, oh boy. Hold on, negative 4 times 34 is not negative. This is probably going to be positive, right? 120 plus 16. 136 minus 6. 130 over 20, 130, so it's basically 130 right there. I think I got it. Did I do that right? I think I did. Yes, feel better about myself. Now you can distribute your 126, of course, and you get your answer. Negative 2, positive 5. Now, before you write this off and say, that is the most complicated thing I've ever seen in my entire life. Actually, it goes very quickly once you get the hang of it. You guys are pretty good at dot products, right? Most of you can do them in your head. So let's just do another example real quick. I'll show you how fast it really can go. Okay? And if you save that fraction out front for last, you don't even have to work with fractions most of the time. So let's just try one more real quick here. Let's say that you had a system 2x minus 5y equals 10. And I don't know, maybe x minus 3y equals 4. You really are boiling it down to this simple problem. Watch. X and y should be the inverse matrix of 2, negative 5, 1, negative 3, multiplied by the right-hand side matrix 10, 4. So I just rewrote the question real quick. It's actually ready to solve. This symbol right here means reciprocal matrix of, okay, or inverse matrix. So I do have to kind of figure out the inverse matrix real quick, but what you do is you put 1 over the determinant out front. The determinant on this problem is, let's see, negative 6, right? Take away negative 5. That's just negative 1. The inside of this thing is sort of a rearranged and negated version of the color-coded matrix, right? So I'm supposed to, let's see, swap the 2 and the negative 3 around, negate the other 2 on the diagonal. Of course, I have a negative 5 already, so I guess that changes to a positive 5. The 1 changes to a negative 1. This isn't that hard. And now you can do your little dot products. Okay, so we have all color code with my highlighter here. So blue times blue, dot product method, right? So that's just negative 30 adding 20, negative 30 adding 20. I'll write my work in here. So we already know that that's a negative 10 up there. And then let's do the other highlighter, pink. How about pink? Oh, that just washed everything out. I don't like that pink at all. Oh, let's do green. So we're doing second row vector with the column vector. That's just negative 10 plus 8, you see. So this is just negative 2. And the minus outside just negates the two answers. 10, 2 is the answer. That's not an ugly method. In fact, it saves a lot of paper space. I mean, it beats some of the other things we did, right? Here's the catch, though. In 3 by 3 matrices, the inverse is notoriously difficult to find. Okay? So what really stinks about this method is it's really best in 2D. But your calculator, here's a cool thing. Your calculator can actually find the inverse of a 3 by 3 matrix instantly. Okay? So you can play around with your matrix buttons later if you want, but you can actually, if you had a crazy system with 10 unknowns and 10 equations, if you could construct the matrix, you could just do, type in the coefficient matrix, and then for a separate matrix B, you could just type in the right-hand side matrix and just do A inverse times B from the home screen. It'll give you all 10 answers. So maybe your variables are like X, Y, Z, alpha, beta, gamma, W, T, L, M, and Q, or something. You know, 10 variables right away, you get them all. Pretty awesome method. So it's very, very efficient for a computer, for example. Obviously, calculator prefers this method. Some calculators can actually do REF, like reducing, row reducing, but it's really hard to do. So, all right, any questions on this method? So that's another method. So tonight you'll be doing one Cramer's rule, one row reduction, and one of these. All right? All right.